Hi, everyone. Welcome back. Our next speaker is an audio engineer, and she has done a lot of engineering for all kinds of production studios in LA. Her talk title is really cool. It's How to Stay Grounded When You Have Zero Potential, which is, I love this title. And it's, she's had a lot of very impressive titles herself for someone who's talking about zero potential. Director of Hardware Engineering, Director of Technology. Please welcome to the Superconference stage, Erika Earl.
Hi, everybody. Thank you, Sophie. Thank you, Hackaday. Thank you all for being here. This talk could easily be a part two to another talk I gave about how mistakes will move you forward. And the reason, what motivated me to want to give this talk, it was a catastrophic power failure on a project that I was really passionate about and volunteering for. And I was responsible for leading the power team. And we had a small army of volunteers who were helping us with assembly. And we had a deadline and a time frame that we needed to get all of this done by. And I didn't plan well. And so while everything was working with our test jigs and our setup with our modules, this was this interactive dance floor and camera wall, 3D camera wall. And as we were testing everything, it was working fine with the power jig that we had and the test rig that we had to measure everything. And then when we went to implement the design, we switched over to the actual power distribution system and experienced pretty sad failures of things not working that I feel super responsible for. So I thought a lot about it and spent a lot of time thinking that perhaps in the beginning of the project, had I planned a little bit better, that I could have avoided that from happening. So ground has always been this elusive word that I've chased throughout my career. In some ways, I feel like it's also offered me the most job security. And a lot of people will just think of it as the ground we walk on, because it's so generic, it'll mean different things to different people. And when I was starting out, I was assembling a lot of kits and didn't really care that much for what 0-volt reference ground was and why it mattered versus what a safety ground was. But I think if you want to start working on circuit board layouts in your own designs, it's really important to have a fundamental understanding that there's a difference and why it matters and how to maybe approach it. So just to give you a little bit of background, music is my love language. Sound has always inspired and motivated everything I've ever done. So the technical parts of me and the desire to learn about anything related to technology and electrical engineering has been born out of this passion for wanting to capture and record and interact with sound. And second to that is the embodiment of it, the control of it. So if you think of a large mixing console, it's the actual human interface to being able to control different sounds and mix them together. And so this passion is what has motivated me to seek out a career as a sound technician, really. Okay, so I'm going to be using some words that you probably are all familiar with. And I just kind of want to cover them really quickly to make the distinction between them. So when I use them, anybody who may not know or be familiar with this kind of jargon can understand what I'm talking about. And you can see in this slide, we have analog ground, chassis ground, digital ground, earth ground. Those are the main ones that you're probably familiar with. But there are also a lot of different adjectives that we'll use. I may or may not get into. I may ask for some audience participation of yay, are you familiar, nay, so I know how far down to go or not go. Is everybody cool with that? Okay. Okay, so chassis is the metal housing or the enclosure, so if you hear me say chassis, that's what I'm saying. That's what I'm meaning or referring to, and the schematic ground symbol is there. When I'm saying AC safety ground, mains power ground, or earth ground, it's really important here that you just know that those are all the same thing. Okay, signal ground is often referred to on a schematic as just G and D. You don't always get the A or the D to understand that there is a difference sometimes, depending on the application. And when I'm talking about signal ground, I'm really referring to 0 volts reference potential. These are the different types of grounding systems. You have power, safety, earth. You have lightning, ESD, radio frequency, and then you have your circuit signal reference. And it's important to know that 1 through 4 all require 5. So it further complicates and confuses things. But we need some point to be able to measure these signals in any of these systems. Okay, so there's 2 primary areas related to ground that I want to focus on. There's the personal safety, which I'm sure many of you are familiar with. This is to make sure that you don't kill yourself, and we'll get into that in a little bit. And then you have signal referencing, which I just touched on, which is the path carrying the return of an analog or digital signal. And then safety also includes ESD and lightning. And I was at the park not so long ago with my kids, and my daughter, Annabelle, found this musical instrument. And this isn't exactly it, but this is the only picture I could find. The one that she was actually playing had this metallic overlay. And she started playing it, and then suddenly she became like this baby EDM DJ sensation because it started malfunctioning, and the switches on it that were supposed to be momentary, meaning like when you put your finger on the switch, it makes the sound. When you take your finger off the switch, the sound goes away, started glitching out. And so suddenly there was this like super obnoxious loop of sounds happening at this park, this public park. And all of the kids are like kind of looking around, and one of the dads looks at me and he's like, "Don't worry, this happens all the time. It'll just turn off on its own." And my daughter, she knows like get down with electronics. She's like looking at me bright red, like motioning me to come over, like come fix this. And so I walk over, I run up to her, and I'm like, "Go down the slide 3 times, come back, put your fingers in your hair, and then touch it again." And she did, and it worked. And then I had to figure out how to convince her and everybody else why I wasn't like a wizard or a magician. So I'm guessing here, and hopefully somebody in the community can figure this out and tell me if this is right or not. But I'm guessing that the metallic overlay had some kind, and the electronics had some kind of capacitive touch happening. And since it was outdoors, that makes sense to me. And so as she charged up her body and then, gave the accumulation of electrons a path to a 0 volt reference or a ground, she was able to discharge that and thus, break the circuit to turn it off. Oh, there she is. So ESD ground. ESD ground provides a controlled path for ESD current that may be on a printed circuit board. The important thing about lightning and ESD ground is that there is a safe path for it. On a circuit board, it can be a guard band, it can be several different things. For lightning, it's usually a spike in the earth, literally, to sink that voltage to make sure that nobody gets hurt. Buildings will put them on all 4 corners, et cetera, et cetera. So these are lethal weapons. and this is, here in the United States, our power distribution system runs off of 15 amps, 120, 125 volts. And my only point for bringing this up is that as an audio engineer, I've seen so many people break off that third power pin because they have ground loops, they have hum. We'll get into some of that later, and that's super dangerous. And it takes like not much to cook your heart meat, literally, like cook it. So safety is important. Okay, back to audio. I want to give you a demonstration of how having different reference potentials can cause issues and noise in your electronics and wreak havoc on the function and operation of it. This is a video that I liked, that I found, that I'd like to share with you. Let's see if I can make it play.
Okay, so for this next experiment, what we're going to be doing is we're going to be making an audible representation of AC power. So what you'll see here is we have a power cord that's plugged into a power bar that's going to the wall, and then we have it going to a transformer. And what the transformer is doing is it's dropping it from 120 volts AC down to 15 volts, which is a little bit more easy for us to manage for our purposes, and it's directly driving the speaker. So what you're going to be hearing is this 60 hertz, 60 cycle hum, which generally is something that we try to avoid. We try to cut out. You know, a lot of gear for music, you know, is made in certain ways so it gets rid of this hum, but we actually are wanting to hear precisely that and nothing else. So when I turn on this thing, the little power bar, you're going to hear it. So here it is.
Okay. How many of you have heard this before? Okay, so everybody's familiar with this thing that we call Maine Tom, or AC 60 cycle hum. And there's different ways that it can travel through electronics. It can jump around and get into your speakers or your headphones, or you can even sometimes just hear your fridge humming at you. How many people have heard their fridge humming at them? Okay, so everybody's pretty familiar with this idea. Well, this is very bad if you're in a recording studio or you're working with sensitive audio electronics. And so one of my favorite stories is,
So for this next experiment, what we're going to be doing is we're going to be making an audible representation.
Is the very famous story about a musical manufacturer that made a guitar amplifier. You may or may not have heard of them. They're called Fender. that decided that they would filter out this, they would come up with a grounding scheme to filter out this hum for all of their audio amplifiers by using a capacitor that was connected to the chassis of their amps. Seems like a good idea, except for the fact that back in the day, we had a two-pronged system, right? So you had a hot, which was often referred the black wire. Sometimes buildings would use color code, sometimes they wouldn't. So you would have this two receptacle outlet that one side has 120 volts running on it at 15 amps, and on the other side you have your neutral or your reference to be able to close the loop and have electricity happening and flowing through. Well, if this capacitor shorted out and a guitar player was connected to it, it could often run on the shield of his cable and electrocute him. And back in the day, you had connectors that were symmetrical on either side, on the two sides. There was no polarization on the design, so you could actually just flip it. So if we go back and we look at this schematic, you can see why they called it the Deathcap. So a bunch of granddaddies got together and changed the power distribution system to have this safety ground that we all see now in the three receptacles. If you don't see it, it's typically because it's double insulated and doesn't require it, and you're going to be protected. And also, like, little external low voltage DC supplies fall within a rating that can't hurt you, and they're designed in such a way to protect you. So you'll still see the two receptacle or two-pronged plugs, but mostly if we have anything that can potentially electrocute us or shock us, it has this additional third pin, which on one side is tied to a circuit breaker and a transformer and a whole system that you can learn about and another time. I don't want to focus on it too much, but just to say and make the point that in the Fender circuit, if you flipped that around, you could see how it would touch the chassis and kill somebody. And then once they introduced this third prong on the plug, you have engineers ripping it off because they have ground loops and hum, and they want to be able to fix it. And some of these old vintage amps still have this cap in them. So it's just something to be aware of in terms of safety when we're talking about safety. Okay, and then signal referencing. So the easiest way for me to demonstrate signal flow is to show you a simple circuit. We know electricity is the flow of electrons through a conductive path in a closed loop, and when the switch is connected, closing the loop, the LED in the circuit will light up. You could replace the load, which is a resistor and LED in this diagram, for any other component configuration and still have the device operate without a single wire touching the earth or a chassis or a metal enclosure. So what I mean to say is that electronic devices can function without any relationship to the earth or a chassis ground. So I've been going back and forth in my mind debating about how far I want to go into electricity and how it works, and using a water bottle to explain potential and difference potential, and using my body to demonstrate current and electromotive force and all of this. And I'm hoping that I can get by with just doing this little dance right now and showing you that it's important to have a 0-volt reference to measure from to be able to determine what our voltages are in our electronic circuits, and that will be acceptable for you all. Me wiggling, shaking, and saying that, you know, if I were to open this cap and all of the water came out of this, it would make a mess out of everything, and how you can think of my body as this force that's creating a current of the water, and so then if it flows out, it's making a mess out of everything, and in, it's contained, and how important it is in electronics to contain your currents and your voltage in order to have your electronics operate. I hope that that was a decent and sufficient analogy for what I'm about to get into. If it wasn't, everyone can just shout, "Hey," and I'll dance for you some more. I think I saw somewhere in this great article online, this engineer was referring to currents and making this analogy to the ocean, and I thought that that was pretty helpful to think of in terms of how important it is to, well, the more control that you have over your current return paths, the more successful you're going to be in your designs. Okay. If I were to ask you, do you believe magnetic and electric fields are capable of propagating in free space, would you believe me? Let's hear it. Yes, of course, right. Because we all have cell phones, we all talk to each other, we understand infrared. We've seen sensors that are doing cool things and lighting up wearable fashions, and yeah, so back to current and controlling. How do you control these RF currents and manage them in a way that will ensure that everything operates the way that you want it to? I included this picture, and that it doesn't interfere with anything. And I included this picture to remind me to explain that part of the reason why all of this matters is because if you ever have any hope to get your product or your device into the hands of many other people, you're going to come into what's called standards testing and regulatory compliance. And you're going to have to make sure that your device is not interfering or harmful to any other device, and how it's interconnected. You're going to have to make sure that it's not going to kill anybody or shock anybody, or that there could be any fault condition that could harm a person. You're going to want to make sure that it doesn't poison the earth. I was working on a project for a console, a multi-touch control surface that's used for production studios, and it involved this 46-inch touch panel that just radiated like a motherfucker. It would just interfere with everything, and we were struggling so hard to try and get it to pass radiated emissions in the lab. And so I decided to try and make the shielding more robust, which we'll get into shielding ground in just a second. And by the enclosure in the metal housing and the chassis had this sort of coat over it. I don't know what kind of chemical it was, but it just made it less conductive, so I wasn't able to shunt that energy and control that RF in any meaningful way based on the chassis alone. So I had to get in there and sand some of the metal components down on the external chassis. And I went to Home Depot and bought all of these Brillo pads and was like, I'm going to basically put a Faraday shield inside the back of this thing and see if that works. And then by process of elimination, take it out. Then I'm going to have to figure out what kind of material I can get to implement into production that meets our costs and actually start shipping these things. But turns out that the Brillo pads were amazing, and we passed with flying colors. And at first, when I showed up there with them all in my hands, I got kind of like funny looks at the lab and like, what is she going to do with those? And then, of course, I meticulously, attached them and affixed them to the enclosure without disturbing any of the electronics, and got us through our electromagnetic interference testing. And so, shielding. Okay, since we all agree that electric fields can travel in free space, we can talk about how I discovered them in the studio, right about the time the guitar player's guitar pickup became a receiver of radio frequencies. So I was in the studio, it was pretty early on, and the guitar player is, we can hear like all kinds of noise in radio stations and whatever and hum. And so the engineer that I was assisting for at the time said, hey, Erika, take a guitar string, tie it to the output jack, and tape it to his stomach. And I was like, what? And I did it, and it worked. And we were able to shunt or divert that current to his body and make it quiet. So there's a simple schematic here that you can see, a single coil pickup, which was acting as the receiver and traveling through the system. And by fixing this metallic steel guitar string to his body, we were able to shunt that current. Later, years later, I found myself as a technician in this really big, beautiful recording studio that had a lot of analog electronics and gear. And I was responsible for making sure that all of the electronics in the building worked and that there was no disruption of creative process for any of the artists that were there and working. And this was incredibly challenging because a lot of these pieces of gear had an original shelf life of like 9 years. The original designers did not expect the components to last as long as they did. And as these consoles and these pieces of gear aged, they started sounding better, so more people wanted to use them. And of course, over time, new technologies became available and people would want to integrate them. And it was really about this time that I was able to zoom in and zoom out to really understand that signal is signal, whether it's on a PC board or it's through an entire room of interconnected devices. And that helped me quite a bit to understand how to manage any kind of interference or noise. In this room, this particular console had a flying fader system, which is digital control for the analog faders to move so that you can recall their positions or your mix positions later. So now we have this mixed signal situation happening, which whenever you're mixing signals, there's always a potential for pitfalls, for these different potentials to cause energy disturbances in a way that becomes noisy or affects your electronics from working properly. In this room, I called this the Beast. It's still one of my most favorite sounding consoles ever, but it's a granddaddy. It's super old, and it had so many grounding issues that were incredibly difficult to solve and find. And so it wasn't until I was able to really understand how to look in and look out that I was able to manage it. And the owner put a spike in the earth thinking that you could just sync all RF to this spike without any understanding of isolation or how any of these things function. And so I bring this up to make the point of the importance of understanding mixed signals, which components you're using, all the way from a zoom-in point, and then zoom out to understand how your designs or devices are going to interact and work with other devices or applications, and how they might interfere and how they might not. So if you even just start at the component level and understand which devices need which kind of grounding methodology, it will make all of the difference later. And then, second to that, think about how it's going to interconnect to anything else, right? How is this laptop going to connect to a peripheral? How are these different devices going to work together, and what might happen? So I love that Hackaday has this article on ground loops, and I loved Bob's quote because it's so true. Ground loops, which I've mentioned before, are, basically when you have two separate devices, A and B, and they're connected to ground separately, and then also connected through some kind of communication cable or any kind of cable that has the potential to carry another signal. So this is another room in console that I was working on, and it has a lot more channels, and each one of these channels is modular. And there was this huge session for this, super fabulous artist, and there was a ground loop that we had to chase, and there were so many different devices that were connected to it. We had, I think for this one, we had like 72 discrete audio interfaces, each having their own DAC, their own converters, their own, we had to figure out clocking. And so now we're mixing analog devices, super sensitive analog audio devices with fast switching and clocks and digital and logic circuits, and they're all mixing together, and we have a ground loop that we have to chase and solve. And so my go-to approach to any of these things is always a visual inspection, checking every single cable, how it's laid out, how it's wired, and then sitting back and considering how things are used. And so in this case, it occurred to me that channel 1 is the most used channel on this whole entire thing, and so I should probably start there. So I pulled out the first channel module, including the large fader, and saw a ribbon connector that had the insulation kind of rubbed off, probably from having this module inserted and taken out so many times for servicing. So, and the ground for this, the signal ground for that module's electronics was on the end and the edge of this ribbon cable the insulation had been rubbed so much that it was now touching the chassis of the console. So, thus creating a ground loop through the whole entire system and wreaking havoc on it. So I put this in here because it's one solution that I think is great for audio engineers who are doing live sound, who are touring, and I wanted to offer this as a solution for you to not have to be unsafe and lift the third ground pin. There are options. They are affordable, and this is an example of one of these devices that uses an isolation transformer that shouldn't degrade your signal if you pay attention, learn your gear, care about it, be safe. So continuing on with mixed signals, it's any microprocessor or operational amplifier. And I just want to say that without an appropriate understanding that there is this difference in ground and understanding that your code is probably meaningless if your hardware doesn't work. And so it's important to be able to work with the materials and resources that you have to figure out which approach is going to be best. This became most apparent to me when I started developing mixed signal hardware and devices for a pro audio manufacturer. And I was responsible for overseeing the installation of our consoles into professional recording studios and connecting them together with other mixed signal audio devices made by other manufacturers. So going back to the zooming in and recognizing, or the zoom in, zoom out approach, I'm calling it. It's having worked with all of these external devices and interconnecting them together that I have a better understanding of it at a component level. And I think it's super important that since we're all seemingly stuck with this generic word for referencing our circuits and have designs, that we make it a point to use an adjective before the word ground, and that we're very careful in how we document ahead, and that we plan for it. You can make a chart. You can make a chart for your pinout, and this is kind of important too because some manufacturers of these chips will recommend that you connect the pins of your analog ground to your digital ground. And that seems counterintuitive in some ways, but it's important for the operation of that very specific chip. So creating a table is one easy and helpful way for other people, especially if you're working on a team, to understand what's what. And I have a note to remind you, which I keep saying it, check your data sheets. A lot of manufacturers will give you recommendations on the method that will work best for implementation of their component and how it can work, specifically related to ground. So there's different approaches that you'll hear: single point ground, multi-point, hybrid ground, and there is no way for me to stand up here and be able to tell you which one of those will be best. There are just way too many components and way too many applications and way too many configurations to do it. My point here is to make sure that you understand that there's a difference and that you're very careful in your planning to choose the right one and what some of these look like. This is a thing that we see a lot, where you have a computer that is grounded to chassis, and then you have a peripheral like a mouse that has no chassis ground, no earth ground, only a signal ground. And then you have a return for it, say USB cable, that is now sending a difference in potential back to the original source, creating voltage noise and messing things up. So if you really get into the theory of it, what you'll find out and what you'll learn is that single point is almost always the best way to go, but it's not always it's not always doable depending on what you're trying to make, and you simply can't. And so one approach is to actually look at your bill of materials and determine straight out of the gate which components are going to force you to have a hybrid scheme, so then you can determine best which method of filtering you want to do, because at some point you're going to have to probably connect your circuit to your chassis ground so that you have more control over RF and interference and some of these other things that we've discussed. And there's a way to do that depending on whether you're needing to it's basically how you want to drive those currents and those returns to make sure that all of those things are working. You can use induction, and there's this great Hackaday video that Bill Hurd starts that talks about induction. I like to think of induction. I like how literal all electrical engineering terms are. I think of induction and I think of my pregnancy, which it was not going so well in that the baby didn't want to come out, and so my doctor recommended that I go to not to the emergency room, but go check myself in and be induced, which is a way by which some doctors give you some pills and then some stuff happens inside your body chemically, and it literally forces the baby out. So hopefully none of you will forget about induction and like that it can force things and force currents to do things that you want them to do. And obviously resistance is like exactly that. It's going to impede and it will help you control that. So this is how I like to think of these things. And my point for bringing all of this up is that the best method is to have a solid single common reference, and a lot of times people will do that attaching it to chassis. And if you have multiple subassemblies, identify them and figure out which components are on those and what's the best method of pushing or impeding these currents around to get it to that common reference so that your circuits operate in the best way possible. So to sum everything up, know your components, identify your subassemblies, figure out what your I/O is going to be, the applications and interconnectivity, and you have this wonderful, huge community of people that you can reach out to that are at every level. So get awkward, be weird, ground is weird, it's hard. Get fancy with your adjectives, use them all the time, put them in your documentation. Let's make it a habit of saying oh, my 0-volt reference or my common ground, or just adding something that's a safety and using them properly. A lot of times you'll start working on a drawing and there won't be the appropriate schematic drawing in the library for you to use. Draw one, make sure that it's right and on your drawings. Add tables, show what's going to what. And I promise you, you will save time, you will save money, and the chances of you actually being able to get your product manufactured will go way up, way up. So yeah, and then be safe, obviously. Be safe and plan. So thanks, guys. That's it. I just want to make it a point to thank